So last time we sort of saw the definition of the Laplace transform, which is defined via this integral. And we computed a couple of examples. A key property to note is this linearity property, which says that it's pretty easy to compute the Laplace transform of a sum. You just compute essentially the Laplace transform of each part. Right. So today we're going to sort of start talking about just some sort of basic inverse transforms. And before we do that, though, you might be wondering sort of how do we know we can even take inverses? I mean, we're taking an integral of a function times something else, but it's not even like an indefinite integral. It's an improper but definite integral from 0 to infinity. I can get tons of different things that have the same integral from 0 to infinity. Well, there's a thing that says called Lurch's theorem that says essentially if I take the let's call this h of t. So if I take, the Laplace transform of some h of t, and I get 0. So if this integral is always 0, then h of t is equal to 0. And there's sort of a technical caveat to that, which almost everywhere. So essentially, cleaning it up a bit just to make it a little easier to read, if this is 0 for every s, then h of t equals 0 almost everywhere. Okay. Well, if I have two functions then that have the same Laplace transform, and I take the Laplace transform of the difference, right? This has to be 0 because I would just get the Laplace transform of f minus the Laplace transform of g. And so what this says is that I always get the 0 integral. And so by, Lurch's theorem, f of t has to be equal to g of t almost everywhere. Right, because f of t minus g of t has to be 0 almost everywhere, so just, move the g of t to the other side. Okay, so this says that, if there's only really one function that can give you a certain Laplace transform, so this lets us define the inverse Laplace transform. So if I have f of s equals the Laplace transform of some function, then the inverse Laplace transform of f of s, which we just denote this, it's just going to spit back out f of t. So looking at the examples we know already for Laplace transforms, this lets us know automatically sort of a couple instances of the inverse Laplace transform. Right, so first, like the Laplace transform of 1 over s, where the inverse is just 1. And this is really just because the Laplace transform of 1 is 1 over s. Similarly, you know, the Laplace transform of 7 over s is going to be 7. Because again, the Laplace transform of 7 is 7 times the Laplace transform of 1, which is 1 over s, and up like that. Okay, so the Laplace transform of 1 over s squared is similarly t squared, and the Laplace transform of 1 over s minus a is e to the at. The other thing that's really important is this linearity property also holds for the inverse. So a times f of s plus b times g of s is the same thing as a times the Laplace transform of f of s plus b times the inverse Laplace transform, rather, of g of s. All right. So let's compute a couple inverse transforms. So we'll start with something pretty straightforward. So all we can really do is sort of separate things into parts that we can identify as inverse Laplace transforms of something. Though I should note, if you Google inverse Laplace transform, like on Wikipedia, it does have a very complicated integral. That integral, evaluating that integral is pretty far beyond the scope of this class, and it does exist, but it's not really used in practice. So we're just going to totally ignore it. So if we split it up like this, then we have 2 times 1 over s, which is just 1, and minus 15 times the inverse Laplace transform of 1 over s minus 6, so e to the 6t. And so the inverse Laplace transform of our original function, 2 over s minus 15 over s minus 6, is equal to 2 minus 15 e to the 6t. So let's look at a slightly more complicated one now. We'll compute the inverse Laplace transform of s plus 7 over s squared. So this one isn't immediately in an identifiable form like the last one, but it's not too bad if we just split apart this fraction. So we have s over s squared over 7 over s squared. So we have that this is equal to the inverse Laplace transform of 1 over s, which we know is 1, plus 7 times the inverse Laplace transform of 1 over s squared, which is t. And so this then is our answer. Okay. Do one more. This was the most complicated one yet. So we're going to compute the inverse Laplace transform of s minus 2 over s squared minus 6s plus 5. And the way we want to do this is with partial fraction decomposition. And so we do partial fraction decomposition. So remember what that is. So we can compute the inverse Laplace transform of something like some constant, over s minus. Oh, so first we got to factor it. So we can factor this as s minus 1 times s minus 5. And we could compute the inverse Laplace transform of some constant over s minus 1, and similarly for some constant over s minus 5. And so our goal is we want to rewrite this as something like this. And here's sort of how we do this. So we're going to take this and we're going to multiply through by this numerator. And what we get is s minus 2 is going to be equal to a times s minus 5 plus b times s minus 1. And there's a couple different options for how to proceed here. I'm going to do a video on partial fraction decomposition later because there's some more complicated scenarios that can happen. But we're just going to sort of match our coefficients. So note we have sort of our s coefficients and our constant terms. Oh, and I did not distribute properly. So we compare coefficients, and we see that we get a system of equations. So a plus b has to equal 1, and negative 5a plus b has to equal negative 2. Can multiply through by both sides to get 5a plus b equals 2. And now I can just go ahead and solve. So I'll get this, b equals 1 minus a. 5a plus 1 minus a equals 2. And so 4a plus 1 equals 2. Solving for that gives me a equals 1/4. Plugging that back in here, I get b equals 1 minus 1/4. So b equals 3/4. All right. So don't necessarily need to show all this work, just sort of doing a little bit of a refresher again. But now we can just go back and we can rewrite our original thing. So we have our original function is equal to 1/4 1 over s minus 1 plus 3/4 1 over s minus 5. And so now to compute this, we just compute the inverse Laplace transform of this new thing. 1/4 1 over s minus 1 We can now split it up using linearity. We note, right, this is the Laplace transform of e to the t, and this is the Laplace transform of e to the 5t. So we can now get our final answer. Is equal to 1/4 e to the t plus 3/4 e to the 5t. All right. So to end this, just going to give you guys one exercise. So we'll have s plus 3 on top, and on the bottom, we're going to have s squared minus 9s plus 18. Right. So pause here, give that a shot, and let's go over the solution. So this bottom right factors as s minus 6 times s minus 3, right? Negative 3 and negative 6 add up to negative 9, and 3 times 6 is 18. So we want to do the partial fraction decomposition, and obviously you need to show more work than this, but we can do it after you get the partial fraction decomposition. you should end up with 3 over s minus 6 minus 2 over s minus 3. And from that, we can see our answer has got to be 3 inverse Laplace transform of s minus 6 e to the 6t minus 2 e to the 3t. All right, leave it there.